when you say smaller matrices, you're not suggesting that the size of the matrix is anywhere smaller than the like the irreducible also have the same order. If it's an n by n matrix, and we are looking at the irreducible representation, we are still going to get an n by n matrix, isn't it?
Yeah, but that's we already dealt with when you looked at projection operators. The projection operators all look like they were the same dimension as the original space, but they were actually smaller rank.
Okay.
A rank means smaller number of zero eigenvalue. You could, when you diagonalize them, you find out that there was a block of non-zero values, and rest was zeros.
Okay.
So in that sense, so they're still carried in this big space, but morally they're very small. And when we write these completeness relations, where we say we take our space and write it as a sum over, spectral decomposition over projection operators, what we are really doing is what Schur's lemma, did we divide it in little blocks.
Right.
Now the projection operators, I tell you, do this measurement, and you'll be able to distinguish ortho and parahelium. They have some, difference properties. But it could be that if I take another measurement, I could still find, more information.
Okay.
So, for example, in quantum mechanics, I can say, well, how strongly is this object spinning? That means I have to measure the magnitude of the spin axis, J squared. And I get an answer that says, this one is spin 1 and the other one is spin 3 in some units. But then I say, what happens if I apply electromagnetic field and da-da-da? That's a different operator, and that actually starts distinguishing how the spin is oriented compared to the axis of my measurement. So I split it in final representations. So there is no guarantee when I taught you projection operators that I was getting irreducible representations. For that, we need to do some extra thinking. So we'll do it 2 times. One is, this orthogonality theorem. Well, Schur's lemma orthogonality theorem, which is totally straightforward, but you will find it abstract and hard to visualize, because how you're going to visualize that an object which has the irreducible label, so that different kinds of matrices labeled by alpha. It's a matrix, so matrix has 2 indices that run over dimension of a matrix, and it has to be evaluated for group element, and there is finite number of group elements, the order of them. So this is some humongous thing that you have to say 4 different things about it. We'll prove that any combination averaged over the group vanishes unless indices line up. So that's not very intuitive to me, but it's beautiful, it works, and that's character orthogonality theory. Then I'll redo it one more time in terms of projection operators, which I find more useful in our research. Hopefully, next time you have to deal with this kind of problem, you'll have a bunch of tools to deal with it, and you'll be able to read the paper that explains how other people do it. So now, it's amazing. It's lots of relationships. It's true for any irreducible representation. And it's not obvious, how do you use this intelligently, because it seems to say that I'm supposed to have an explicit representation, because whenever I write these indices, it says I've chosen my coordinates in which I've written this representation mu. It's a bunch of numbers, with square roots of 3 and God knows what. Because that's obtained by going to unitary representation. So that, that's amazing that matrices will satisfy this, but it looks like lots of work to use it. So then the next amazing thing happens, which is sure realized that the simplest possible invariant under the group, which is a trace of a matrix, suffices. So I don't need to have all this explicit d mu nu matrices with 1,000 things. I can just their diagonal parts summed, and that that I find surprising. That turns out to suffice. Why do I find it surprising? When you're given some matrix, obviously the diagonal summed of the matrix is invariant under similarity transformations. I'll just remind you, you know it, but I'll just say it again. If I define character.
Can I ask a quick, I guess, clarifying question as far as terminology goes?
Yeah.
So when what you're calling a class, is that kind of like the idea of a conjugacy class that is like defining a normal subgroup of this finite group?
No. So that that's what makes this thing a little bit confusing, because class, for example, all subgroups have to include identity.
Right.
The big groups. But there's only one class that has identity as its element, which is identity itself. So they're distinct notions.
So then I guess these classes are basically the partitioning cosets of the group then? Because a normal subgroup would include that specific one that has the identity, but the other ones I guess wouldn't be, but they would be considered cosets.
Yeah, so that's that's a third thing that we haven't used cosets. So it's tedious group theory because you have to be very precise about all this words. So on the abstract level, you have one integer, which is order of the group. You have subgroups. Then you have cosets, which are like conjugate of the whole subgroup.
Right.
Now, only one of the coset conjugates of identity is subgroup. The other one's a partition of your world into subgroups, and that tells you that subgroup dimension or order of the subgroup is always divisor of the order of the group. That's what you get out of cosets.
Right. Okay.
Then you have class, which is yet another partition.
Okay.
Right. It's not cosets, and it's not, these are all on abstract level, and it's not the subgroup.
Okay.
It's what kind of things you're doing. You're either flipping or running around, or something more complicated if you're looking at molecules and 3 dimensions or God knows what, right? Okay. There are lots of finite groups and they have different classes. So that's yet another thing. Now, class turns out to be the important notion when you go to representation theory. So that's now, everything I said so far was abstract. Representation theory says I have to implement symmetries, and often I do it by matrices. Matrices can be diagonalized. Sets of matrices can be block diagonalized. Every matrix individually in the subject, because it's either unitary or Hermitian, can be diagonalized. But you're trying to simultaneously diagonalize as much as you can all matrices that represent actions of your group. And the best job you can do is to block diagonalize them. And that now is what characters are doing. They are a property of representation, and they are unique property of irreducible representation, no matter what you started with. And diagonalization takes place by using characters to go from your group elements divided in classes.
Mm-hmm.
So classes of group elements to irreducible representations, which are, the blocks of a matrix, block of your matrix representations.
Okay.
So let's see, I don't know how to help you more.
No, that's fine. So the classes themselves are not necessarily subgroups. They're just kind of their own.
No, they're definitely not subgroups.
Okay.
I just told you.
Yeah.
I mean, identity is a subgroup, so that's the only example. Right?
Okay.
There's only one subgroup, which is a class, and that's identity. Everybody else is different.
Okay.
And, group might not have subgroups. Well, that's an interesting question.
Well, I feel like a group would have to have at least the trivial subgroup.
Yeah, it always has trivial subgroup and group itself. But if it's of a prime order, then it doesn't have any other subgroups, meaning order is a prime number.
Right. Yeah.
Because discussion with cosets tells you that subgroup must be it has to have integer order, but that order has to be divisor of the order of the group. The only groups I can think whose order is prime in my mind are cyclic groups, but I don't know which are simple, abelian, where everything kind of agrees. Number of irreps is same as number of classes. Classes are very simple, and there are no subgroups. So you can see the number of classes is very different than number of subgroups, because the only subgroup is the trivial one, the identity or whole group.
Right.
But number of classes in this case is the order of the group itself.
Okay.
So class is different. Subgroup is, a bunch of people it's a clique in a high school, people who only hang out with each other. And class is different. These are all people who have certain income and nothing else in common or something.
Okay.
And character is a property of an individual realization of a member of a class, shared by everybody in the class. All rich people are, equally honorable, let's say. Same character.
Okay.
If that helps.
Okay.
These three is the triangle, but hexagon is
Right.
D6.
Okay.
The big deal is that one is odd and one is even. So the odd ones have only one kind of symmetry axis because it goes through a vertex and an opposite face. But the even ones, like 4, 6, 8, etc., they have two kinds of flips.
One is about
Through the long axis,
diagonal,
and one is the short.
The short one being
Go through the half interval between two vertices.
oh, okay.
It's kind of obvious when you look at the picture. So then they have odd and even have different numbers of irreducible representations. So the odd ones have everybody has one symmetric, one antisymmetric. But then because of this axis, you actually have 4 kinds of one-dimensional representation for even, and rest are 2-dimensional, blah, blah, blah. It's actually easier to look at Fourier modes first, discrete Fourier modes, and then count, how many are combined when you flip them. The first point is kind of, trivial, just to understand the trivial case. The second one, this determinant, usually is just 1 or -1, so there isn't much going on with it. But just to get used to the idea that trivial representation is also important. Actually, they tend to be the most important ones, the fully symmetric one in applications. The second one is, just get different idea that you can represent group in different ways. And then, do the thing with determinants, traces, characters, and see where it's reducible or irreducible. So, and the third one is the whole deal. So if you do the third one, you've done everything. So first part is kind of easy. They both have 6 elements. So you just have to show that multiplication tables can be related to each other one-on-one isomorphically. The second one is, 3D, again, an example of representation. The next one is a good example of, splitting a representation in reducible parts. This is like the first non-trivial example ever. So you understand that, you get 2 blocks, 1-dimensional, 2-dimensional block. So I think this should all be quite easy, I hope.
Mm-hmm.
But I suggest working through the Dresselhaus or any other notes to the level of studying exercises where you use characters to split up higher dimension representation in smaller pieces.
Irrep and or the Darstellung which we write, is that a large matrix which contains all the groups, or are we referring to? I'm trying to understand this in the matrix sense of it. So we write one matrix for each group element, or do we write the whole, the big matrix consisting of all the group elements? Which of those would come down to an?
No. Matrix is always a 1-to-1 on group elements.
And
so there is always, that's what makes it hard. There is always H if order of group distinct matrices or less if it's not faithful representation. But the statement is that all of them can be simultaneously block diagonalized. That's totally not obvious. Right?
All of them together, when we put them, they can be block diagonalized.
Separately, and there's various sums of them if you wish.
So if I take one group element and I write a matrix for that, I can block diagonalize that single matrix.
The non-trivial part is that when you take the next group element, totally different large matrix, it can be block diagonalized in the same shape.
Same shape.
Yeah, so you have blocks within group acts within each irreducible space separately.
So if I have a 6x6
doesn't
matrix,
mix up different blocks.
So if I have a 6x6 matrix and just assuming that my irrep contains of a 3x3, a 2x2, and a 1x1, then each element.
There is a law against it.
Oh, there's a law against it? Okay.
Yeah, the sum of dimensions of the representation will prove it has to be equal to the order of the group. Some of the orders, dimensions of irreps.
That I did. I think if it's a 6x6 and I have a 3, 2, and 1, I'm still following the law, isn't it?
Yeah, no, that's illegal. No, it's only thing that's allowed is 1, 1 plus 2 plus 2.
Oh, okay.
That adds up to 6, and the
right.
sums of the squares satisfy the law.
Okay. All right.
It has a name of I forget. It's not Laplace, but Lagrange. I don't know. It's Lagrange's theorem. It's one of the French mathematicians.
Okay.
We'll prove it. It's a trivial consequence of full reducibility.
Okay.
But that we still have to do.
So what I'm trying to understand is, when you said earlier that the number of classes is the same as the number of the irrep here is in terms of a matrix, is it?
By the way, I'm wrong. You could have something that's, if there were a 3-dimensional representation of the D3 then, if it existed, it could show up. But D3 has only one and two.
Okay.
It has only three classes and three representations.
Okay. The three classes being identity, flip, and rotation.
Rotations, yeah.
And
three irreducible representation and average with weight 1 and average with weight -1 whenever there's a flip in the group element. And then harder to understand two-dimensional representation.
Okay. So the irrep, when you say irrep, it is a combination of all of these, or
no, irrep is one of those.
Single one of those. Okay. So I was confused earlier, thinking that when you say irrep, it is the set of all the fundamental or the most basic ones, which can be used to build the other group elements. So that's
irreps are the atoms from which you build molecules. Yes.
Okay. Now I think I do get that. At least for D3, I do get the sense of why the number of classes.
Yeah, I mean, it'll be useful. We'll work through several examples of which this problem set is one, the simplest one. But we'll work by hand through a few physical examples.
Okay.
Just to get a hang of it. The amazing thing is that it suffices to know characters to do this. That's again one of those things that a priori I wouldn't expect.
That at least for me, it's not intuitive. That
no,
I just know the character.
That one took until 1888 to discover or something, or fairly late, in the second half of 19th century. So it's, Newton didn't do it, and Italians didn't do it, Babylonians didn't do it, Chinese didn't do it. So it's not totally trivial as far as I know. So it's actually mathematics. It's this, step-by-step kind of mathematics I'm reproducing for you that got to that point. Intuitive, it's not, I think.
So as a rookie in LaTeX, how does one refer to an equation, figure, or section and creates like a link?
LaTeX has something called a cite and ref. It has a way of cross-linking it. I'll give you a link to a template which has examples of it. That's what's so much better about LaTeX than, let's say, Word, because I watch people who have strayed into biology suffer through this thing. So it's very good in cross-referencing, and it's very good in kind of using mathematical notation. I think it's still a necessary tool for mathematicians, physicists, and certain kind of engineers. Biologists have to suffer for, having sold out. They use Word, and it's such a nightmare. I mean, I see it with my colleagues, because every time something happens, everything gets reformatted and everything flies someplace else. They spend so much time, and references and all that shit is so complicated because it was never meant to do science. Class and coset.
Yeah, I think
these are the worst. Class is all morally equivalent actions, flips versus rotations. Formally, it's defined all the elements that stay within a set when you apply conjugacies. Conjugacies mean when you apply going someplace and coming back. Whenever you sandwich it between group element, it's inverse. That's a conjugacy. And class has a property that it's the minimal set of elements that don't go anyplace else. They stay within under conjugacies. But you have a good geometrical intuition about it because it just means, if you have three axes to flip across, then you can use rotation to align the axes that you want to flip and then flip and then come back. So you have a table and there are 17 axes because you're on 17 N-gon. and you would like to flip around 12 axes. What you do is you rotate by 12, you flip the thing, and you rotate it back by 12, and that'll be the correct answer for flipping around that axis. So it says the flip around any axis is equivalent. Now, when we add it, if you have a, even polygon, let's say with 6 faces, that happens a lot in physics. Then there are 2 different kind of axes. There's axis that goes through vertex and the axis that goes through half interval. And, so you either have to rotate so that the vertex comes to your table, or you have to rotate so that, you get aligned by the half of the interval, and then flip. So there are 2 kinds of flips. So there will be different classes in that case. So not all flips belong to the same classes because they're long axes and short axes, and they're physically different. Just to give you an example, it's not just simple flips versus rotations. You have to think a little harder. Basic ideas are simple, but the details kill you because there are so many details. But it's beautiful, it works, It's not like real life. This is theory that works. Okay, bye.
Professor.